Okay, let's talk about now about stochastic models. I will just describe these models very briefly because they are a huge topic that will take a whole course by themselves to cover, since they have a lot of implications. They are also quite useful in quite a few many situations. They're more accurate than usual SIR models. So, why stochastic models? Well, until now we consider just models in which there was no chance, no probability, no uncertainty. Given a set of parameters, we were able to predict exactly the trajectory of the epidemic. Well, this is not actually true in real life, especially when we consider a situation in which we have a small number of individuals, or when we consider the initial phases of epidemics in which we have a really small number of infected individuals. Well, in this situation, the chance and the probability are extremely important. For the same set of parameters, for the same pathogen, you can either have a big outbreak exploding or nothing happening at all. Because, for example, the person that is infected by chance that they didn't meet anyone else, or he died before meeting someone else, or any kind of event can happen. So let's get more into details. Instead of focusing on rates like the normal SIR models, in this case we focus on individual infection probabilities. The usual approach is to consider each infection as a random event, a yes-no event with a given probability, a little bit like a coin. Such events in probability theory are described as Bernoulli random variables. But a Bernoulli random variable is an event that is described by a probability. It can have just a yes-no outcome. So a big difference from the stochastic models and the classical SIR models is that even the R naught by itself cannot give us a guarantee that there will be an outbreak or not. So the usual threshold R naught over 1 or below 1 is not by itself enough to give us a 100% probability that there will be or there won't be an outbreak. We won't speak anymore about precise numbers like the cumulative number of infected at the end of the epidemic, or the final susceptible fraction, or the peak prevalence. Instead of having single numbers, we will have probability distributions for each of them. For example, let's observe this simulation. We generated a number of epidemics using always the same R naught parameter and the same number of initial infectious people. But you can observe that the final size of the epidemic, that is the cumulative number of infected at the end of the epidemics, can change drastically between simulations. So we have a group of simulations that produce a final epidemic size between 500 and 700 individuals. But then we have also a big group of simulation in which there was no epidemic at all. We had 0 new cases apart from the initial cases. So you can see that even with a R naught that is above 1, we can have totally different situation. And of course, in real life, we won't observe all of them, but we will observe just one of them. And we will never be able to understand which kind of R naught produced the epidemic that we observe if we just use data and not general knowledge about the pathogen that we are observing. So is the R naught totally useless? Well, not exactly. Even if R naught will not tell us about the exact will not predict exactly if there will be an outbreak or not, it will help us estimate the probability that the outbreak will happen. Instead, we will talk in this situation about the likelihood of an epidemic outbreak, that is the probability of the outbreak happening. And this number, E, actually depends on R naught. It can be computed as 1 minus 1 over R naught, elevated by IO. This IO is the number of initial cases that we introduce in the population and that can start the epidemic. As you can see in the plot on the right, we have a number of R naught values, and a very low R naught like 1.5. Even if we have such a low R naught with a high initial number of infectious cases, then the probability of having outbreak is still very high. But if we have an extremely high R naught 20, which is something hardly seen in nature, and then we have just one case at the beginning, still we don't have a 100% probability to observe an outbreak. So summing up, even with R naught above 1, the epidemic may die off. If R naught is below 1, then the epidemic die off with 100% security. I won't show here how I derive these two other results, which take in account the percent of susceptible or vaccinated population, but it's just an extension of this formula, in which as they are not considered the population which is totally susceptible, we will put here the RF or RT, which is the effective reproductive number, which consider also the proportion of already immune population. And putting RN or RT here, we can observe that having a partially resistant population decreases the chance of the epidemic even more. And also, it can be estimated that while we reach a level of vaccination higher and higher, even if we don't reach the immunity threshold, the herd immunity threshold, we can still observe the epidemic disappear. Again, because it's a stochastic event, so once the R naught gets closer to 1, even if it's still above 1, we can observe the epidemic totally disappear.